is the chair of mathematics at Bard College, and he will be speaking about the Borda Count. So take it away, John.
All right, thank you so much for the invitation. And I'm going to just make sure that my screen, hopefully my screen is visible to everybody. So thank you all for the invitation to come here and speak today. I'm going to talk about a project that I did with two people. One is Sam Shao, who used to be in the math department at Bard, but who is no longer here. He's left academia at this point. And my senior project student, my senior thesis student, David Paulette from 2010. And in fact, what I'm going to talk about today, there are actually two papers. One of them is a pure research paper, and one of them is actually a paper that appeared in Social Justice and Mathematics for the Classroom. So there's actually a version of this paper that is aimed at how to teach this material to non-major mathematics students. I'm not going to assume that anybody knows any voting theory before we start, and I'm going to take us basically from the very beginnings to the statement of the main theorem. I'll also say that I'm not an expert in this area of research. My area of expertise is really in number theory, and this is I teach a class for my non-majors on math and politics, and I had a senior who was interested in exploring a research project, and along the lines of what Jonathan said in the talk this morning, this is really a fertile ground for student research. So let me give you this overview. So I'm going to tell you about voting with two alternatives. So in the world of voting theory, we call our candidates, or the things that we're deciding between, alternatives. And there's a real dichotomy between voting between two people or two things and three or more. Okay, I've picked and chosen my examples really carefully to make sure that you actually see some of the distinctions. And then the main thing that I'm going to talk about today are when your preferences are partially ordered, meaning that how do I vote if if I can't vote, if I see three candidates, A, B, and C, if my true preferences are not A above B above C, but maybe there's a tie. And that's truly what I believe. If I'm asked to submit a ranked ballot, then I have to submit something that's disingenuous. Okay, so is there a way to vote when I have partially ordered preferences? All right, so that's the outline. So what I'm going to start with an example of voting with two alternatives. So say my alternatives are red and blue. So there's two people voting for office, red person, blue person. And what is voting? Well, voting is collective choosing. And suppose there are n voters. And with these two choices, what would a ballot look like? A ballot looks like, who do you want to vote for? Okay, the red person or the blue person. So a sample ballot would just be, you declare who you're voting for. Okay, and so what is a social choice function or a voting procedure? It really is a function that inputs. So there should be n ballots here, and I input the n choices of everyone's choices, and I've chosen this example. So what if the function does the following? Everybody voted for the red person, and the outcome is the blue. Okay. So this would be, for example, this would be like a voting procedure in which y'all vote for who you want, who you think is the best candidate, and the taller person wins. That's what this function does. And so you can ask, is this a reasonable voting function? And the answer is, well, it depends on what you mean by reasonable. Is it a well-defined function? Yes. We know there's no ambiguity in what the answer is going to be. It's going to be the blue person, or it's going to be the taller person, right? So it is well-defined. But in some sense, it doesn't represent the will of the electorate at all. So maybe there are additional notions of mathematical fairness that you can impose onto certain voting systems. Okay, so one voting system that comes to mind, right? The way that we're all thinking is, why not just use majority rules, right? So if we're voting between two people and we just want to choose whoever has the most number one, or the most votes, I guess there's two people. And so why majority rules? Why do you like it so much? Well, here's why you like it. It's anonymous, meaning that you can't tell who voted for whom just based on the outcome. Right? So you have an election, your vote is private, and there's an outcome, there's a winner, and based on just based on who won, you can't tell actually how any of the individual voters voted. Okay. It's neutral. Now, neutral, so I'm going to do my best not to put any mathematical formalism in this whatsoever. There's a formal mathematical definition of neutrality, but I'll just write it down for you since it's not something that's very familiar. And it just says that all alternatives have an equal chance of winning before voting starts. That was not the case with our taller example. When the taller person is going to win, no matter what, all alternatives do not have an equal chance of winning before you start. Okay, you can, if you want, so really what this is about is that this is invariant under permutations, but I'm happy just to leave it like this. And it's non-manipulable. So if you want someone to win in majority rules, you have to vote for them. You can't gain by submitting a disingenuous ballot. So these are some of the reasons why we really like majority rules. Okay. So I want to jump to like the main theorem in this subject. And this is what happens when you vote when there are more than two alternatives. So there's a theorem, not this one. There's a theorem due to May that says that voting between two alternatives, there is essentially one and only one way that's going to be anonymous, neutral, non-manipulable, and that's majority rules. So there's like a perfect answer for voting when there are two people, two alternatives. When there are more than two alternatives, the famous theorem in this area is Arrow's theorem, which says that there are many examples of how to vote, but none of them are perfect. So there's something called the Borda Count, and we're going to talk about that today. And there's single transferable vote, and there's instant runoff voting, and there's all these other ways to vote, and none of them are perfect. And so actually there is one perfect way, and this is what Arrow's theorem says, which is Arrow says that this is the dictatorship theorem that says that what you do is you choose a ballot at random, choose a top person on that ballot, declare that to be the winner. And that satisfies all mathematical fairness axioms, but is not something that we would ever use. Okay? So that's Arrow's theorem. Now, 20-something years later, Young comes along, and Young is an economist, and writes another seminal paper that says this: okay, maybe they're not perfect, but some really are better than others. So let me give you an example. And that's the Borda Count. So I'm not going to assume that anybody has any familiar with what the Borda Count is. So I'm going to work through this example with you. So, the way the Borda Count works is in vertical lines here, these represent a ballot. So every vertical arrangement of letters represents a ballot. And so my alternatives are red, green, and blue. And what the Borda Count does is it scores the candidates. So we get 3 points for people in the first row, 2 points in the second, 1 point in the third. And so what I'd like to do is I'd like to score these ballots with you. So the red candidate gets how many points? 3 and 1 is 4. and 2 is 6, and 3 is 9, and 2 is 11. So the red person gets 11 points. The green person gets 2, 4, 5, 6, and 3 is 9. And the blue person gets 1, 4, 7, 9, 10. And so most points wins. That's the Borda count. Okay. And so if we had 4 alternatives, we would rank them, we would give them points between 1 through 4 and do the same thing. And then just most points wins. Okay. And so when I teach my course in math and politics, my students love the Borda count. They gravitate towards the Borda count. And so Young anticipated this, and this is the main theorem from 1974, which says that there is a unique way of voting that satisfies all of these beautiful, which I will not define for you. Maybe I'll say 1 or 2 words about what these mean later. But there is a unique social choice function, a unique way to vote that is neutral. That's the everybody has equal chance of winning before we start. Consistent. That means that if two disjoint populations vote for the same person, then the union votes for the same person, for that person. Faithful, cancelable. More mathematical terminology that I'm not going to impose on you in this short amount of time. But Young says, if we can't be perfect, the next best thing we can be is the Borda count. Okay. So this brings me to what I want to talk about today. And so this actually, this happened in real life just the other day. It was warm enough so I could finally walk to the ice cream place down the street from me. And I know that they have soft serve, and I was in the mood for soft serve. And I know that here are my preferences when it comes to soft serve and soft serve alone, that there is a unique best choice, which is vanilla. And I know that I prefer vanilla to chocolate. And I know that I prefer vanilla to strawberry. And those are the 3 flavors of soft serve at my local ice cream place. And so, this truly is my preference. Now, what if this was a ballot and my true preferences were these for 3 alternatives, and I was forced to submit a ranked ballot? Then I have to submit something untrue. And so this was the starting question that my student David Paulette had was, okay, is there a way to impose a system of voting that would allow for the voters to submit diagrams that look like this for their voting preferences? Okay. So here's an example. So suppose we have 5 alternatives, A, B, C, D, and E, and I've color coded them like this in all the examples that come. And so this is what a sample ballot might look like. So let me tell you about what this sample ballot, how I read this sample ballot. I prefer A to B, and I prefer B to D. I prefer A to C and C to D. I can't tell you anything about B and C. I have no preference between B and C, and I've never heard of E before. So I go to vote, and I literally have never heard of alternative E. So I actually don't, so what's the truth? The truth is, I don't know how they fit into this other hierarchy. So if these are my true preferences, is there a way for me to vote? That's the question that my student David Paulette, he brought this question up, and then he just got playing around with these ballots. So here are the 2 questions that we want to answer. Is there any way to do it? And if so, is it any good in the sense of Young's theorem? So I'm going to just post this for you right now. Here's a sample election of 6 ballots. So this is 6 people trying to choose between 5 alternatives, A, B, C, D, and E. And from this, I'll bring it back in a little bit later. From this, can you determine who ought to be chosen if this is the true preferences of all 6 people in our population? If these are their true preferences, who should be chosen as the winner or tied for the winner or not? I'm not telling you how to do it yet. So how? So this was the first result that my student came up with. And so so what he says, all right, look, I want to start scoring ballots, just like I score them in the Borda Count. And what I do is I'm going to put a weight. So the weight is the number that I'm going to put onto the ballot. And the weight is going to be 2 times the down set. So the down set, so I mark this in red and I'm circling in blue. I mark this in red. So I have this one alternative here. And how will I score them? I will score them by saying it's 2 times, the down set is the number that are below it, linked by edges. And the incomparable, this person here would be incomparable. So the score that I'm going to put down is 2 times the number below in a chain, plus the number which are incomparable. And we're going to do some examples so you see it in action. Let's score this ballot. Okay, so E, let's work with E. So who is below E? Who is in the down set of E? B, C, D, and A are all below E. So there are 4 people below E. And it's 2 times that down set, 2 times that number, and none are incomparable. So E will get a score of 8. B, there is 1 person below B, A, and 2 that are incomparable. So I get 2 plus 3 equals plus 4. So this number 4 represents 2 from A and 1 point each from C and D. And you see that C and D also get 4. A, there is no one incomparable to A and no one below A. A gets 0 points. That is how this ballot would be scored. Okay. So here are some other examples. So let me just point out a couple of these. This ballot over here, this could be considered apathy. You don't care. All right, you've never heard of any of these people, or you just don't care who wins. And let's just check that this is consistent with our formula. If I single out this person over here, well, how many are incomparable? 1, 2, 3, 4. Let's look at this ballot over here. So notice that these 3 alternatives all have different number of points. So let's try to explain it. So this person is 4 versus this one is 3. Both of them are only above one other person, but 3 has someone above them. 3 has 2 people above them, 4 only has 1. So 4 should be ranked a little bit better. So it should have a higher score. 5 and 4, or sorry, this one and this one, each have 1 person above them, but 5 is ranked above 2 people, whereas 4 is only ranked above 1 person. So that's that discrepancy in scores. Something you might notice about this, add up all of the points on each ballot. And I think in each case, you're going to get 20. I think in each case, you're going to get 20 points. And that ends up, it's non-obvious, but that ends up being a consequence of that formula, 2 times the down set plus the incomparable set. In fact, you are not penalized in assigning scores this way. So every ballot is worth the same number of total points. You can see that in these 3 examples, and that's a general consequence of the theorem. So we call this method of scoring ballots the partial Borda count, for lack of a better way to do it. a lack of a better name. And here's the question: is it any good? Right. So at first, so my student David. So David came up with this way of assigning points to ballots. And you could, I'm going to scroll back up. So apologies if I'm going too quickly. Why not 3 times the down set plus the incomparable set? Why not pi times the down set plus e times the incomparable set? Why not? Right. So what about that? There's something about being ranked below, which is counting twice as much as being incomparable. Okay, so why? Here's the main theorem. So the main theorem says there is a unique social choice function on partially ordered ballots that is neutral, consistent, faithful, and cancelable, which is the partial Borda count. This generalizes Young's theorem. This is literally word for word Young's theorem, except that if you just remove the words partial, then this is Young's theorem. Okay. So I would like to point out that linearly ordered ballots, the one that we usually think of, ranked ballots, are special cases of partial ballots. So this theorem encompasses Young's theorem and generalizes it to all partial orders. So there's 2 things that I'd like to say. So I know that I'm going to be out of time in just a minute. So there's 2 things I'd like to say. One, this theorem is really not a theorem about voting. This is a theorem about functions on partial orders, where the inputs are partial orders and the output is a partial order. This is a theorem about, this is a combinatorial theorem on functions on partial orders, satisfying these combinatorial and set theoretic criteria. Right? I think before I said this consistency. This says that if I have 2 non-overlapping subsets, 2 disjoint subsets, both of whom select the same candidate, their union must as well. Okay, so these are set theoretic and combinatorial statements, and so this is really this is really a combinatorial paper. Here's the thing I love about this theorem the most, and this is the most surprising thing to us. So nowhere in this theorem did we ever say that your function had to be based on scoring a ballot. Right? Nowhere did we, so you can imagine, right? So our theorem says the partial Borda count, this method of assigning 2s and 1s to the down set and the incomparable set, that is a way of voting. And it is the unique one that satisfies these properties, but you actually recover the scores from the combinatorial and set theoretic data. So that was when we proved that and sort of figured out that was sort of the underlying thing. That was when we knew that we actually had a really big result on our hands. So I realized that I am out of time, so maybe I'll just stop right there. Thank you.
So thank you very much. Applause for John Cullinan. Are there any questions, please? I'm not sure. Do people with questions just speak out, or do I have to allow them to speak in some way?
I think people can unmute themselves.
Yeah, if you have a question, just please unmute yourself.
I'm gonna stop my share so that maybe I can see people better.
I have a question. I'm not sure if it's a good one though. I'm curious sort of like how granular is the act of assigning weights to these things? So in the sense that if I gave you 5 numbers that add up to 20, obviously if I gave you all 4s, we know that the ballot producing it was aptly, but can you always reverse engineer the graph?
No, you cannot. So there are different graphs that will have there are different graphs that will have the same weights. And in fact, so I lied just a tiny bit. So in fact, it's I can take any affine shift of those 2 1. So all I need is that the ratio of the incomparable and the down be 2 to 1, but I can take any affine shift of that, and that works as well. Yeah.
Cool. Thanks.
Yeah.
Are there any other questions?
Very nice talk. I'm
Thank you.
very intrigued by this result. I wanted to ask if you compare in the universe of possible partial voting methods, cumulative voting, where you basically take that 20 and each person decides how to assign the numbers.
Mm-hmm.
Is it clear that even if you were in the universe of that the only way that you get something that satisfies those fairness axioms is if they're exactly assigning it like a partial Borda count, as opposed to just picking numbers like, I want to give this person a weight of 7, this person a weight of 6, because that's just how I feel.
Yeah, I love that question. And what I'll say is stay tuned, because we actually have a senior working on that exact same question right now. So actually this whole topic has actually spawned numerous senior theses. So all students at Bard write a senior thesis, and you can see that there are many questions that just pop out. So I can't answer that for you right now, but I am on a senior board later next week, and then I can maybe answer your question then.
Great, thank you.
Yeah.
All right, let's thank Professor Cullinan again, and we will recess and come back in 1 minute for our next talk.